So welcome to Chapter 3. So Chapter 3 is not going to be a super long video like Chapter 1 and Chapter 2. We had a lot of initial ideas to introduce. This chapter has a lot of important ideas as well, but the Pearson material, particularly your labs, will go in depth into one of the most important ideas that we cover in this chapter, which is Kepler's laws. So we're just going to do a little introduction to Kepler's laws, talk a little bit about this idea of Ptolemy versus Copernicus. So one of the big ideas here about Ptolemy versus Copernicus. So both of these are astronomers. Ptolemy was very smart and lived about 1800 years ago, or 1,800 years ago. And he came up with the Ptolemaic view of the solar system. So in the Ptolemaic view of the solar system, Earth is at the center of the solar system, and everything revolves around it. So we have this very smart guy. He's Greek. Very smart Greek guy. Lived about almost 2,000 years ago. And this is the idea that dominated through the Middle Ages. People in the Middle Ages were absolutely dependent on the Greeks for a lot of this basic knowledge type stuff. Now here comes a different smart person. This is Copernicus. His real name is Nikolai Copernic. It was very chic when he lived about 500 years ago. And it was very chic very cool when he was alive to make your name sound more Latin. But he wasn't Roman. He was Polish. So this is a Polish astronomer. In the early days of the revolution that overthrew the Greek models of astronomy in Europe, Polish and Danish astronomers were very dominant. So Copernicus was a Polish astronomer that lived about 500 years ago. And he said, this doesn't work very well. The center of the solar system is the sun. So this over here, this model is what's called a geocentric model. Not the only geocentric model, but a geocentric model. And this is a heliocentric model. And these stems here, this is geo is the stem is Earth. So that's geocentric is Earth is in the middle. And helio, that means sun. That means the sun is in the middle. And it turns out this guy, Copernicus, was the one that was right. But it's not immediately clear that to people who really understood the system, they were like, oh my gosh, that makes so much more sense in the way that we've been doing it. But it's not intuitively obvious. And the reason that it's not intuitively obvious is this big important key idea, which is the planets. So the stars have a straight line path across the sky, while the planets zigzag. And that zigzag motion has a particular name. That's what we mean when we say retrograde motion. Retrograde motion is a very fancy way for saying it's zigging and it's zagging. Let me grab out my red pen. So it's an apparent retrograde motion. It apparently moves backwards and forwards in its path. So Ptolemy came up with this idea that, they're moving backwards and forwards in their paths because planets basically move it through the sky like a little corkscrew. So the Earth is in the center, and planets are literally going woo, 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 woo. Copernicus's model is much more simple, but it's much more subtle because you say, well, how do I see these curlicue patterns? How am I seeing this corkscrew pattern for the motion of the planets? that, and planet literally means wanderer. I mean, this is something that all the ancients have brought up. When we go over another one of those mythology videos, we're doing a mythology video in this unit, and we'll do it in a later unit as well. The motion of Venus, for example, is backwards and forwards, and and they're called they're called planets because planet means wanderer, that they have this weird zigzaggy motion that the stars just don't. So how can things be moving in a perfectly orderly circle and it makes it look like things are zigging and zagging? So this is going to get fixed on your copy. My copy has retrograde motion written down here. I'm just going to scribble that out and put retrograde motion up here. You won't have to do that because yours will already be corrected. Now, to understand retrograde motion, we first have to understand the definition of two different groups of planets. So that is the inferior planets and the superior planets. Now, this does not mean that they have a complex, okay? The inferior planets are planets closer to the sun than Earth. The superior planets are further from the sun than Earth. Now, when you're thinking about superior versus inferior planets, can you think of a superior and an inferior planet? Can you give me an example of an inferior planet? Just take a moment and think about it. And can you give me an example of a superior planet? Dora the Explorer moment. Very good. So inferior planets, some examples of the inferior planets include, well, we only have two. We have Mercury and we have Venus. I'm going to capitalize that before English fans freak out on me. Mercury and Venus. And then for our superior planets, that includes everybody else. Mars, Jupiter, Saturn, Uranus. Uranus is superior. Ha, ha, ha. Get ready for your Uranus jokes. Anyways, Neptune. So any of these, so when we're thinking about the explanations for retrograde motion, okay, we need to consider both of these. So one important key here, an important key idea is retrograde motion occurs with both inferior and superior planets. I'm filming at a friend's house, and apparently there's like a drag race going on outside. It's gone fast and furious outside the house, but we're keeping trucking because it's not the easiest thing to film these things. Okay, so retrograde motion, I'll refilm it someday later, but for right now, this is what we're rolling with. So retrograde motion occurs with both inferior and superior planets. All planets exhibit, and this is because all the planets are moving at a different rate along their track. Along their orbit. So inferior planets, basically if it's closer to the sun, it's moving more quickly on its orbit. If it's further from the sun, it's moving more slowly on its orbit. Okay. So closer to the sun, faster. Further, slower. That's going to be really important when we try to describe retrograde motion. So I'm going to scoochy this up a little bit. I'm going to draw two diagrams. In one of them, Earth is going to be inferior to, in one of them, Earth is going to be inferior to the planet that we're observing. And the other one, Earth will be superior and the planet will be inferior. So keep in mind the position relative to the other planet is going to change. So the first one, number 1, I'm going to actually give you a whole other blank page for this because this is running out of room. I'm just going to add an entirely new blank page to this unit in here because quite clearly this is going to take more room. So on the next page, you're going to draw your sketch of retrograde motion because we're going to need a lot of room to do this. Or room will definitely help, and I will give you that extra page. So for this one, we're going to have a superior planet. And we're going to start out in the middle here. We're going to have, this is going to be the sun. And then let's see now. That'll work. So I've been liking the green being Earth. So we're just going to have Earth be green again. There we go. Okay. And then for our superior planet, let's do that nice teal color. So this orbit here will represent Earth's orbit. And this over here will be a superior planet. So for example, Mars would be a superior planet. Okay. So we're going to draw multiple Earths and multiple superior planets. So we're going to start off. Now, all of these are orbiting counterclockwise. So I'm going to just let's do 7 dots here, representing 7 positions of Earth. The spacing counts. Make sure that you have a good amount of spacing in between. Here, I've left like a little bit thicker than a thumb. And we're going to call this position 1, 2, 3, 4, 5, 6, 7 for Earth. Okay. Now we're going to go back and we're going to do for our superior planet. Now our superior planet is moving more slowly. So I'm going to draw them. I'm going to have their position 4 the same as our position 4, but they're going to be spaced closer together. And that geometry is important. So 1, 2, 3, 4, 5, 6, 7. So it's going to look like that. Okay. Now we're not going to actually draw Elliot this time. We're going to imagine Elliot standing on each one of these Earths and looking up at that superior planet. And I'm going to draw an imaginary night sky in the background over here. So these are the stars against the backdrop. And that'll make sense in just a moment. So at position 1, Earth is looking at here. So this is where Earth sees the planet at 1. At 2, because it's looking here, it'll be up against that backdrop over here. At 3, it's going to look like this. At 4, and now all of a sudden we can see it. 4 makes it really clear that 1, 2, 3, 4. So we're going this way, and now we're zigzagging back again. Okay. And now 5. Now we're zigzagging even back again, loopity-looped. Remember, the Greeks thought this was literally a corkscrew. 6. And now our last one over here. Is 7. Okay? So this is what's causing that loopity-loop. So we can say 2, 3, all the way down to 4, now down to 5, now up to 6, now up to 7. Okay? So it's basically curled in on itself. It's moving back and forth. Now for an inferior planet, it's pretty similar. So we're going to draw this very similarly for our inferior planet. I'm going to still have 2 circles. I'm going to have my Earth circle. I'm going to make it green because once again, I just feel like, I don't know, green just feels earthy to me. Come on, wheel. There we go. And now that we have that one, now I'm going to draw my inferior. Inferior feels, I'll just do it a bit pink this time. There we go. Draw that all the way around there. Okay. So, for the inferior planet, now remember, if it's closer to the sun, it's going to move more quickly. So this time, I'm going to draw my Earth. This will make sense. And our sun is still in the middle here. So these are our orbits. This is my sun. Okay. And when I sketch this, I'm going to have my Earths more closely spaced together than my inferior planet. So this is my inferior. This is Earth. I'm going to start it on the outside edge this time. We're going to have the projection over here. So and remember, it's counterclockwise. So this would be position 1, 2, 3, 4, 5, 6, 7. And then for our inferior planets, I'm just going to draw a 4-point to line up like that. But now I'm going to space them out more. So this will be 3. This will be 5. 2. 6. 1 and 7. Okay. And now, same idea. Night sky is in the background over here. And once again, I play connect the dots. So now I'm just using my blue to connect my dots. This is going all the way down here, so that's 1. Glad I went for a totally separate sheet of paper. Connecting 2 to 2. So looking out from Earth into the inferior planet, that's 2. That's 3. I'll go in the same direction still. Now we have 4. We can't really see 4 because the sun is in the way, but it disappears. And now when I'm looking at 5, now 5 is way over here. And we're going to see that when we look at a video on the Aztec myths associated with Venus, which is an inferior planet. Now it's swinging back around again. And now we have 7 over here. So just like the superior planets, it's been bouncing all over the place. So 1, 2, 3, swing back around for 4, 5, swing back around again, 6, 7. So we can see that it's zigging and zagging back and forth. So now let's move on to Kepler. So we've talked about the smart but wrong Greek guy Ptolemy and the smart and right Polish guy Copernicus. This is another one that's really smart and also right. This is our German astronomer. And he lived about 400 years ago. So we're talking about 100 years after Copernicus. Now, if you want to hear the exact date, Copernicus. If you want to hear the exact dates, you're welcome to look that up in your book. But I just want to give you a perspective. I don't care. This is not a history class. You do not need to give me, like, the Battle of Hastings was 1066. Like, I don't care. What I do care about is that you have some kind of vague idea of, like, okay, where are they in this history of science? So, and Kepler came up with what would be known as Kepler's laws. Basically taking the observations and the ideas of Copernicus and kicking them up a notch. So we have 2 kind of shapes right here. Okay. So this right here, this is the one you've known since grade school. This is our good friend, the circle. This one over here is an ellipse. Now, an ellipse and a circle are pretty similar. Both can be formed by tying a string to a nail and drawing all the way around. But the circle is if you tie the string to the nail, okay, and you just draw one string and you go all the way around that one nail. Now, if that string is attached to 2 nails, in other words, like it's one string, like imagine like two nails in there and you tie a string and you make it kind of loose and you tie it in on the other side. That's what we're talking about when we're talking about with an ellipse. And if you draw that tight and you draw all the way around, you will draw an ellipse. So where those nails are called the focus, plural foci. Rather than just having a radius, it has 2 axes. The minor axis, which is the short way, and the major axis, which is the long way. So if you kind of think of it like an egg, the long way across the egg is the major axis, the short way across the egg is the minor axis. And the eccentricity is basically a measure of how stretched an ellipse is relative to a circle. So why do we care about this? And this is really subtle, because it's not like the big deal here is that no planets move like this. No planets move in a circle. Nope. No planets moons, etc., comets, anything move in a circle. They all move, they all have elliptical orbits. And really, and we may get into this a little bit later on, I'll try to find a good video on this. What's really going on is, actually, there's some good videos in this attached to the Pearson, so I may actually assign those for extra credit. As we're going to learn with Kepler's first law, the sun is at one of these two foci. So what's really going on is that the planet is continually rising up. It's like you know how you toss a baseball? Like imagine walking while tossing a baseball. What you're going to have is this series of parabola, right? So what's really going on is that the planet makes this arc and then falls past the sun. Swings past and keeps falling. Swings past and keeps falling. So really what's going on is that this is this shape that's traced out from the planet falling past the sun and just keep on missing it. This is really subtle. It is amazing. So Kepler is a crazy dude. His mom got accused of things like witchcraft. He worked with this crazy Danish dude named Tycho Brahe that had a gold nose. I mean, just like read up on Kepler. He is among the weirdest and wackiest of the scientists. And he used some really precise measurements, an incredible deduction, because it's not like some of the, like for example, Earth is almost a circle. The difference between the major and the minor axes is only about 6%. So, that's pretty subtle, considering that people are just using pens and paper and very basic telescopes. So, pretty cool. Let's keep trucking. Make sure we understand these laws before I let you loose. So, Kepler's first law, that's what I just referred to. So, planets and other objects travel in an ellipse with the sun at one focus. There's nothing at the other focus. It is an empty second focus. Okay, there's nothing there. But the sun is at one of the two foci. Let's take a look at the second law. Pretty straightforward. So, let's just go a little bit more in depth into this first law. So, let's pretend that the sun is over here. Okay, the sun is at this focus, and there's nothing at this focus. Now we have an ellipse that we can label with two important parts of it. The first is the perihelion, where the planet will be closest to the sun, and the aphelion, where the planet is going to be at the furthest from the sun. So, for example, for Earth, aphelion is in January, whereas the perihelion is in July. So, the perihelion is the point. So, this is the point where the planet is closest to the sun. And this is the point where the planet is the furthest. Now, Kepler's second law is a little bit tricky, and we're going to use color, as we often do. We're going to use color to help clarify it. So I'm going to mix colored pencils And that's a very nice pink. I'm going to use that pink. And then I am going to use this teal. Okay. And then this pink and this teal. So I'm going to use colored pencils and pens to try to clarify this. So the big idea with Kepler's second law, equal areas equal equal times. That's the big summary here. Now, what does that mean? The rate of the planet's motion is dependent upon the area in which, so if you imagine like a string attached to the sun, or even better yet, a rubber band, because it's going to need to stretch to the aphelion. So imagine that the planet's going around in this rubber band. It's attached to this rubber band. The speed of the planet is going to be determined on its orbit. It's going to be determined by the area swept out in the ellipse by that rubber band. So let's make that a little bit clearer, because that's probably about as clear as mud. So this right here is our sun. So we'll just color this in yellow. That'll be our sun. Or orange. I guess that's more orange. Now I'm going to take, for this area, I'm going to use this lovely aqua green. You can use whatever color makes it clear for you. For me, perihelion says aqua green. I don't know why. I guess it's an artistic thing. And I'll do pink for the aphelion. So here's the key. The aquamarine area, this area here, these two areas are equal. So the time it takes the planet, this little planet here, to go from A to B is exactly equal as it takes to get from C to D. Okay? So the time between A and B is equal to the time from C to D, because this color area and the pink area are equal. Now, that's the in-depth what's going on with Kepler's second law. The big key takeaway I want everyone to get, no matter how good you are at math, the big idea that I want you to get is that planets tend to move faster. Planets are moving faster closer to the sun and more slowly further from the sun. That's the simple take-home message of Kepler's second law. Now, you can calculate exactly how much more slowly and how much more quickly and all that kind of stuff. But for this class, this basic intro class, if you get this, you're like 95%, and don't stress too much about if that's freaking you out. Okay? So basically the planets are going like woo, 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 like that. Okay? Now Kepler's third law is even simpler in the sense that it's just a simple ratio. Okay? So this is the P here, P squared. This P is the planet's orbital period. In other words, how long it takes to go around the sun. That's the fancy, that's orbital period is a fancy way of saying the planet's year. So how long does it take the planet to go around the sun? Okay. For example, it takes Earth about a year. It takes Mars about twice as long. Okay, about 2 years. So it takes other planets much longer. So the superior planets much longer, and then the inferior planets like Venus and Mercury have much shorter years. So, because they're, as we discussed back with the reasons for retrograde motion, is that they're orbiting more quickly. So this is what this is really saying. That's the key home here. Okay, and then A is the average distance from the sun. So this is the precise mathematical relationship, and I do believe in one of your online labs you do need to calculate this, but the take-home message, once again, if math is not your jam, if you're like, Dr. E, I was promised that this was not going to be a super heavy math class. So you will get 95% of the way to Kepler's third law if you just remember planets closer to the sun have shorter years. In other words, time it takes to go around the sun. Than ones further away. And once again, we're using our orange highlighter to say that is a take home. That is, no matter how cozy, comfortable you are with math, that is going to make sense to you. Now, this is how you calculate that exact relationship. And this is the relationship that implies it's this relationship that causes this retrograde motion ultimately to happen. So I hope that makes sense. If it doesn't, that's okay. That's what you pay me for. So don't be afraid to reach out. I hope you enjoyed chapter 3 and module 2. And I'm looking forward to seeing you in future modules. Keep in mind that we do have a question based around a little mini quiz question in the workbook based around Kepler's second law. So if you're struggling with this at all, particularly this one about the comet, don't be afraid to reach out. So be kind to you and be kind to each other, and catch you in the next video.